All right, so we did example 1. Let's keep practicing, see if we can get the hang of this. We're going to read carefully. I've got 4.50 grams. So grams tells me that that is my mass. So 4.50 grams. I've got pure gold absorbing 276 joules. So that would be my heat. What is the change in temperature? So delta temperature is my unknown, and I'm given that the heat capacity of gold is 0.129 joules per gram per degree Celsius. All right, so you've got your givens, you've got your unknown. Now I'm going to write my equation. The heat equals m cat. And then now I'm going to just substitute in what I've got. So I've got 276 is equal to my mass, 4.50, times my capacity, 0.129, times my change in temperature. So all these are being multiplied together. I want to get rid of these, so I'm going to divide, all right, by 4.5 and 0.129. So this is a number, and I'm dividing by that same number. So I have to do that on both sides. All right, and I'll just put that into my calculator. All right, so I get my change of temperature is 475 point, I'll go ahead and just go to the tenths place, so I'll say 0.5. And then temperature is degrees Celsius. All right, and that is it. That's very good. So if I wanted to do this with 3 significant digits, I would make that 476 degrees Celsius. All right, let's go to the next one. And again, if you know algebra, you can solve anything. All right, I've got grams, so that's my mass, 355 grams. Here's my heat, so that's Q, 9750 joules. And I'm looking for the change. It says, what is the change of temperature? So delta T is my unknown. And I'm given the capacity of water, the heat capacity. Notice it's really big. Water takes a lot of heat. That's why it takes so long to watch it boil. All right. So now I write down my equation. Q equals m cat. And now I substitute. Let's see, 4.18. I'm taking off the units because I'm just doing the math. All right, now these are all multiplied together, so I'm going to divide to get rid of the 355 and the 4.18. Okay, so I'm dividing by this number, whatever is 355 times 4.18. All right, I'm just going to do that on my calculator. Okay, so you take the 9,750 divided by 355 and then divide by 4.18, and you get 6 point, let's see, let me do 3 significant digits, so 6.57 and the units for temperature is degrees Celsius. All right, so notice it did not change the temperature very much, okay, because water can absorb a lot of heat. That's what keeps our Earth so wonderful, so nice for us. All right, so here we go. Now we have a piece of metal with a mass of 4.68, and that's grams. It's absorbing 256 joules, so that's heat. 256 joules. Temperature is increased, so that's a positive. Change in temperature is positive 182 degrees Celsius. I didn't have to subtract like I did last time because I only have the one, it just tells me the change. So, and the question is, what is the specific heat? So that's C, the specific heat. Sometimes it'll look like that, is my unknown. So let me just write down my equation. Heat equals m cat. Substitute to, oops, why did I put that? We'll make that a 256 equals 4.68 times C, I don't know, times the temperature, the change in temperature, which is 182. Okay, even though these are in different order, remember multiplying is commutative, so I can just divide by 4.68, that goes away, and by 182. All right, so these will be multiplied together, 182. All right, so on my calculator, I'm just going to do 256 divided by 4.68, and then divide by 100 and, oops, I put in the wrong, 182. So do it on the calculator. Make sure you can do it. A lot of people mess up. They do all the algebra, etc., and the chemistry, but they don't work their calculator right. I'm going to round that last digit to a 1, and that was the heat capacity. So the unit for that would be grams per, oh no, sorry, it's joules, right? Heat capacity is the joules per grams per degree Celsius. So it's important to write that unit just like you always do. All right, so when a substance is undergoing a phase change, does the temperature change? And if you look here, you can see that when you're changing the phases, the temperature is staying the same. All right? When I'm changing from a liquid to a gas or a gas to a liquid, all right, I've got a horizontal line. There's no slope, so that means there's zero temperature change. So no, it does not have a temperature change. So that means if I'm using this formula, if this is 0 and I'm multiplying times C times M, that is always going to be 0. All right, so the energy would always be 0. So we need a different equation. And here we go. We have something else we're going to learn about, a new word, enthalpy. All right, and so that is the change in energy, because if we go back to our graph, the temperature is not changing, but the energy, right, this is the heat added, the amount of energy, the amount of heat that I've added is changing, okay, from here to here, all right, and from here to here. All right, so when I have a phase change, temperature is staying the same, but the heat is changing, the energy is changing, and so that is the enthalpy. And the equation for that would be this one. So we still have Q for heat, and we still have M for mass. But now we have this delta H for heat, right? It's the change in heat between the products and the reactants, all right? So we can do this because if you have an equation, you can solve any problem. So it says, what is the heat? So that's my unknown. Q is my unknown. I'm vaporizing something, so I'm going from a liquid to a gas, right? So that is, which is what it says, liquid to gas. So that's a phase change, right? So I'm going to use my enthalpy. And I need to know the mass, just like before. And that's given to me because it's grams. So 950 grams. And I know that my delta H, my change in enthalpy, is 333.51. It's positive, and that's joules because it's energy per gram. All right. And we're not talking about temperature because the temperature is staying the same. So now I'm going to write down my formula. Q equals, and now it's like Ma. There we go. Trying to find Q. I know the mass is 950, and the change, or my change in enthalpy, change in the heat, energy, is that. And so I'll just put that into my calculator. And I get that my energy is and then that would be, energy is joules, right? Because I took grams times joules per gram, so my grams cross out. Remember good old dimensional analysis? And that gave me joules. All right, so that is my answer. And if I wanted to do that in, let's say I wanted to have, just let's say 2 significant digits, that would be 3.2 times 10. Let's see, would we move it 1, 2, 3, 4, 5 times 10 to the 5th joules for Q. If I wanted to do scientific notation, and that gives me 2 significant digits. All right, you'll be having multiple choice questions on your test, so you just have to be able to go back and forth. All right, so here we go. I'm melting, so that is a phase change. Okay, so that means my temperature is staying the same, so I have my enthalpy here. All right, notice all the clues are in the question. If you read it carefully, it tells you what to do. Calculate the heat. Okay, that's my unknown. Grams, that's got to be a mass. Fusion, so that's another word for going from liquid to solid. Or no, I'm melting, I'm sorry, solid to liquid. All right, solid to liquid. So that is my enthalpy, and 2483.20 joules per gram. Okay, my knowns, my unknown, and now my equation. Mass times change in energy there, change in the heat, and then substitute. I don't know Q. I know the mass is 75, and the enthalpy is 2483. Okay, I'm just going to do that real quick. You do that too on the calculator. And I get that the heat would be, and that would be joules. Okay, Awesome. Very good. And if I wanted two significant digits, I would make that 1.9 times 10 to the 1, 2, 3, 4, 5 joules. All right. So let's summarize what we just went over here. Here is our heating curve. Notice when you have the change in temperature, right? When it's a solid or a liquid or a gas, and so it's changing temperature, you use the MCAT, all right, because you have a change in temperature. When you are doing a phase change, you don't have a change in temperature. So that's where you talk about the change in energy, which is your enthalpy, all right, or the change in heat, and which is the Q equals Ma. All right, so how does a chemical reaction occur? Well, you have your reactants, then you get you add some heat to get your chemical reaction, and which gives you an activated complex, and you end up with products. All right, you saw this when you were learning in biology about substrates and enzymes. All right. The activated complex is where you have the substrate and the enzyme together. You have one big thing. All right, it's unstable intermediate between the reactant and the product. All right. What energy is involved in a chemical reaction? Well, we have just like we had the law of conservation of mass when we were balancing equations, we have the law of conservation of energy. The energy also cannot be created or destroyed. All right. It does change forms. All right, or it can change forms, but it cannot be created or destroyed. So we measure energy in the form of heat. So you have reaction energy. The heat of reaction, which we talked about just a second ago with enthalpy, that is the heat content of the system. All right, you have two kinds of reaction energies. You have endothermic and exothermic. All right, exothermic means you start out with the energy of your reactants, right? It's 150 joules here. I'm going to add some energy, add some heat to make this reaction happen. I reach this peak here, this activation complex. All right, I reach 200 joules, and then my reaction all the reactions happen. The new products are formed, and they have this energy down here. All right, this would be 50. The energy of my products is 50. All right, so now what happened was I have a difference here of 100 joules. I had 150 joules, now I have 50 joules. So I have 100 joules out here. All right, that is added, you could think of that as a product. Okay, this heat enters into the system here. All right, it goes out. Your test tube will feel hot if this is happening. You have your products in the test tube, and then you have heat if you change the temperature. The heat is released. That's exothermic. All right. The energy of your products is less than the energy of the reactants. That means you have an exothermic reaction. All right, because we have the law of conservation of energy. That heat did not disappear. It changes, it's released into the system. All right, so the heat becomes a product. Endothermic, exo means going out into the system. Endo means it's coming in. All right, you're taking in the heat. All right, so it's going to feel cool, your test tube is. So we start out with our reactants down here at 100 joules. All right, we add a lot. We add 300 joules of energy. So we get up to this activation complex here. And our reaction takes place. And then we end up with our products here at 300 joules. So the energy of the products is higher than the energy of the reactants. So they actually absorbed the energy. All right. And so that means that the energy is now a product. Or excuse me, it's a reactant. It's on the left side of your equation. All right. So the energy of the products is more than the of the products over here is more than the reactants, and that means it's endothermic. Your products absorbed the energy from the system. So heat is a reactant. So does this happen spontaneously? No. Remember, what you saw was there had to be an activation energy. We have to make things happen. Otherwise, reactions would be happening all the time. If you're going to boil a pot of water, you don't just let it sit there. You have to add heat. You have to add energy. All right, the activation energy is the energy needed to jumpstart a chemical reaction. So I have here in this diagram, I've got my reactants, and they have an energy level, potential energy of 150 joules. All right. The activation energy that I have to put in to get to my activation complex, which is 200, I have to put in 50 joules to make something happen here. All right, notice this is exothermic because the products have a lower energy, so that means this heat is going to be released. Okay. This is endothermic because I started out with 100 joules. I end up with my products at 300 joules. So that the heat is over here. It gets absorbed in the reactants side of my equation. All right, and notice I have I had a lot of activation energy that I had to put into that. Collision theory, you have your atoms, molecules. It's just like it sounds. Collisions is banging, things colliding, banging into each other, crashing. All right, so when atoms, ions, molecules crash into each other, a chemical bond can form, all right, if there is enough kinetic energy. If there is not enough kinetic energy, the molecules and ions collide, but they just bounce apart. And again, you've seen, these are things you're familiar with in your life. Activation energy, if you want something to stick to the wall, you throw it hard. All right, it takes a lot of energy. Activation energy is the minimum amount of energy that these colliding particles are going to need in order to react. So there are factors that affect the reaction rates, and we noticed this in the lab we did when we put the foil in and we watched it change color. Right? Changing color is a chemical reaction. And we noticed that if we increase the temperature, the reaction, the color changed quicker. All right, so increasing the temperature, it increases the number of particles that have the energy to react. All right, so the reaction rate goes up. All right, if you increase the temperature, you increase the reaction rate. Concentration, if you have a lot of particles in there, they're going to collide, all right, more. And so if you have a high concentration, you're going to have a high collision, so you would increase the rate that of your reaction. Particle size. The smaller the particle, it's going to have a large surface area. All right. And so that means it's going to increase the reaction rate. So this might be harder to remember because you're going to have a small particle means you have an increased rate. And we kind of know that actually. If I wanted to dissolve a sugar cube, I know that if I smash it into smaller bits, those smaller bits are going to dissolve faster, and they would react faster. All right, and the reason for that is if you have small particles, you have a large surface area, which is something you have to really think about for a little bit. A catalyst is a substance that increases the rate of reaction. It speeds things up. A car is a catalyst. It gets you somewhere where you're going faster. Okay? So a catalyst that's a new word. A catalyst increases the rate of reaction. All right. And again, going back to biology, your enzymes are catalysts. They make things happen faster. Equilibrium is when the reactants and the products have a happy medium. They're balanced. And so the chemical reaction will go forward and in reverse. And notice you have this arrows going both ways. Forwards is left to right, and backwards is right to left, kind of like if we're reading. So it's kind of like a seesaw with equilibrium. All right, so because if I change it, right, if I change something on one side, it is going to move the system. It's going to make things go forward or backward, okay? So, for example, if I want to change the system, what I could do is I could add or take away things. I could change the concentration. I could change the temperature. By increasing or decreasing, adding or taking away heat. And pressure, I could increase or decrease if I'm talking about gases. So change in concentration. So if I increase A and B, the A and B are on the left, so they're my reactants. If I increase my reactants, well, that's going to move it forward. All right, that's just intuitive. That makes sense. Use your gut. If I've got more reactants, then I'm going to try to get more products. If I increase the products, that would move it to the left, and so that would make it go backwards so that I get more products. More. If I increase the products, then I want to get more reactants. All right, so more reactants moves it forwards, more products moves it backwards.